Suppose if I have to design any combinational circuit with the help of multiplexer, so how we can do that? As we know that whatever the combinational circuit we want to develop, all the function, all the combinational logic circuit has some function. Okay, whether I want to make like half adder, full adder, subtractor, anything, any kind of logic function. So all the logic combinational logic circuit must have some function that we want to develop. Okay, so if you you know the function, so here we will try to see how we can utilize multiplexer to design those functions or those combinational logic circuits. Okay, so let us try to see. As I told you, suppose I have a function f, okay, and in that function, it is really very important like how many variables we have. Suppose the function could be like x and y. So what it means, it has two variables. There could be another option like a function could be x, y, and z. So this could be another kind of thing. So here we have a three variables. So similarly, we can have the n number of variables to make any particular function. Okay. Now, once we are ready with how many variables will be there in that function, we can select which of the order of multiplexer is required to develop that function. Let me repeat it again what I'm saying. Suppose I have a function which is fxy and another function which is fxyz, and the other function could be like wxyz and so on. Okay, so if we know the function, if you know the number of variables, then after you can decide what is the order of multiplexer that we need to design that function. Okay, so now suppose I have this f is equal to fxyz, where we have a three variables. So let us assume this n is equal to 3. The number of variables are 3. So to design this function, we can use the multiplexer having n control signal. We can use the multiplexer having 1 minus 1 control signal, and this is up to 1. So the number of control signal in the multiplexer is having n minus 1, and if we try to reduce by 1 each time and up to 1, so all these kind of multiplexer can be utilized to develop this one. So if I have n is equal to 3, means the multiplexer having 3 control signal, multiplexer having 2 control signal, and the multiplexer having 1 control signal can be utilized to design or to implement the function having 3 variables. And similarly, it is applicable for other cases. Like suppose if I have 4 variable function, in that case, there are 4 possibilities that we can have. Like one will be 4 number of control signal, another will be 3, then 2, and then it is 1. So 4 means we need 16 cross 1 MUX. Okay, 4 means 16 cross 1 MUX. 3 means this is 8 cross 1 MUX. Okay, 2 means 4 cross 1 MUX, and 1 means simply 2 cross 1 MUX. So if I have a function having 4 variables x, y, z, w, x, y, z, so in that case, I can implement those functions either with the help of 2 raised to 1 MUX, or with the help of 4 raised to 1, or 8 raised to 1, or 16 raised to 1. So this is important thing that we should consider. So keeping all these things in our mind, yeah, so the best combination, or like someone may ask, suppose I have a function and I have to develop based on the multiplexer. So which of the combination will be the best? Okay, either this one, or 8 raised to 1, or 4 raised to 1, or 2 raised to 1. Okay, which of the multiplexer I need to use, because I have 4 possibilities. So how I will decide which of the possibility is good to design that combinational function or that combinational logic? Okay, so here we will try to see what are the which one is the optimum one, and how much complexity we can see inside the system and outside the multiplexer. Okay, both we will try to see all these things. Okay, so let us try to continue. Okay, so one more thing I just wanted to tell you. Suppose I have I just told you, if I have a two variable or three variable. So if I have a three variable, so the first possibility could be like I can use the multiplexer having three control signal, means 8 raised to 1 mux can be applied to this implement this function. Similarly, 4 raised to 1 can be used and 2 raised to 1 can be used. Now let us try to see how we can do that. Okay. Uh, but as of now, I will tell you about this one, 8 raised to 1, and then later on I will tell you how we can use 4 raised to 1 and 2 raised to 1. 4 raised to 1, 2 raised to 1 and 8 raised to 1 means what? The number of inputs in the multiplexer. Okay, so if you see here, if I am able to design this function like three variable function with the help of 8 raised to 1 multiplexer, and we know that in 8 raised to 1 multiplexer total number of inputs are 8, and the total possibilities out of this function is also 8. So what it means? It means that all the combinations, suppose I have a function something like f x y z, and that function is, let us assume, summation of m 0 1 2 5 and 7. Let us assume this is the function, and if I want to use 8 raised to 1 multiplexer to implement this one, so what we need 8 input multiplexer. Okay, so suppose if I need 8 input multiplexer, so 1 2 3 4 5 6 7 and 8. Okay, let us assume this is the I0 to I7. Okay, and here I will have three control signals. Okay, and then I will have one output. Okay, let us assume the control signals are x, y and z. Now what will happen? The minterms which are available in the function like 0 1 2 5 and 7, these all minterms are available. If all these minterms are available, what it means? We will connect those inputs to the logic high. So I0, I1 and I2, 5 and 7, these all will be connected to the logical 1, and all other will be connected to the logic 0, and this is how this function will be. Okay, so based on this combination, xyz combination, this is how you can make the function with the help of 8 raised to 1 mux. So this is the easiest way. Okay, but of course there is no designing part. Based on the minterms available with us, directly we have connected all the inputs accordingly. Okay, so better, instead of 8 raised to 1, we can go for the other kind of arrangement, which is a 4 raised to 1. I will again tell you about 2 raised to 1 as well. So we'll see one by one. Okay, so if you have any doubt on this at this point of time, you can ask the questions. Otherwise, we'll move ahead with this 4 raised to 1 kind of multiplexer. How we can implement the three variable function with the help of 4 raised to 1. Then later on, we'll talk about the three variable function implementation based on 2 raised to 1 mux. Okay. So yeah, so this is all about the implementation part. Now let us try to see how we can do that. Yeah, so suppose if I want to implement this three variable function with the help of 4 raised to 1 mux, so the number of columns which we can see here, the number of columns represents what is the number of inputs. Okay, so all these common columns indicates the inputs. Okay, and accordingly we will try to see here. Okay, and of course you need to remember here is like the sequence is like 0 0 0 1 1 0 and 1 1. Here like if I have a three variables, so variable could be a b c x y z, anything it could be. So 0 1 0 and 1 for the a, and for bc I will have 4 combinations. So this is how I can get all these possibilities. If you try to see what, like suppose the combinational logic, like any of the function whatever it is given, that can either be in the SOP form or it could be in the POS form. Okay, so let us discuss both. So initially let us consider, I'm considering the SOP form. Okay, in the SOP form, how it will look like. Okay, this a and b, like a here, this particular term indicates the a complement, this indicates the a. Here I have a bc which is 0 0, so I this indicates b bar c bar, This indicate B bar C, BC bar, and BC. And the order of inputs are something like, because I just told you the number of columns that represents how many inputs are there. So this particular table indicates I have a 4 columns. So this can be implemented with the help of 4:1 MUX. Whatever the designing part we are doing over here, this is utilized to implement the combinational logic with the help of 4:1 MUX. If there are something like this, there is also possible like we can have a table like this. Okay, because I have a 3 variable, so I can keep 2 variable here and third variable here. So it will be like 0 1 0 0 0 1 1 1 1 0 and 1 1. And because I have only 2 tables, 2 columns, so to implement this table I may need 2:1 multiplexer. Okay, so this is how we can make it out. So based on the number of columns, we decide what is the order of multiplexer that is needed to implement this function. Okay, so yeah, we will discuss these things later on in more detail. Okay, so now once we are ready with this function, and if you can see, if you try to write the number, so the number can be written something like 0 1 2 3 4 5 6 and 7. Okay, now what is the input? Because as we know, as I just told you, the number of columns indicates the input for the multiplexer. So I will have 4 inputs: I0, I1, I2, and I3. So these all are the number of inputs. Okay, now what input I will connect? So important point is, if I have a given a function, let us assume any function, something like 0 1 5 and 6. Okay, 0 1 5 and 6. Okay, so suppose let us assume I have a function something like this. Okay, so what I the min terms which are available, I need to encircle them. Okay, so this is the encirclement point. Okay, next one is this one is the encirclement point, next one is this one encirclement point, and the next one is this one is the encirclement point. Okay, so as we see here in this table, we can see the 4 possibilities. First possibility is the upper part is the encircled. Okay, the second possibility is both the parts are encircled, means all the like the elements in the column, all the elements in the column is encircled. Third one is the lower part is encircled, and the fourth possibility could be none of the part is encircled. Okay, so how we can write all those things? What is the meaning of all these encirclements? Okay, so if you see here, if the upper part is encircled, it simply means that the A bar should be connected to the I0 input. Okay, A bar should be connected to the I0 input. Yes, one more thing, whatever the B and C is here, these two terms should be considered as a control signal or the select line for the multiplexer, and this term indicates the input line. Let me repeat it again. Whatever the variables we have kept in the columns, like here in this direction, these two, or how many it will be have, that will be considered as a select line for the multiplexer. So B and C are the select line, and here the variables which are available in this side, these will be considered as an input side. Okay, so the BC will be connected to the select line, and A will define the input. Okay, so that is why we are talking about what will be the input. So if the upper part is encircled, then A bar, because this is associated with the A bar, so A bar will be encircled. A bar will be connected to the I0. Okay, similarly, if both are encircled, then directly logic high will be connected to the input. If lower part is encircled, then A will be connected to the input 2, and if none of the terms are encircled, in that case logic 0 will be connected to the I3. Okay, so this is what we can expect. We can connect the multiplexer based on the combinations. So if you have any doubt on this SOP form, then you can ask the questions. We will take the example, then I will tell you how to do that one. Okay, it's not that much difficult, it's very easy actually. Okay, so anyone has any doubt on this, on SOP form, then you can ask the question. Okay, if there is no doubt, then let
So,
us, yeah, please.
so you said BC represents the control signal, but
Yes.
earlier you said it represents inputs I0, I1, I2, I3.
No. Input BC, this combination B bar C bar, that indicates the I naught. This combination indicates, like, this is how we decide, like, for if the BC is equal to 0 0. Okay, so that indicates I0. Okay, so I0 will be transferred to the output. If BC is equal to 0 1, then I1 will be transferred. So the input
Okay,
is
sir.
decided by the BC.
BC acts as a control signal.
Yes.
Oh.
Okay, fine. So so this is all about the, now let us talk about the POS form. Okay, suppose I have a POS form. So how it works? Okay, again we can have, I'm just considering three variables. So for the POS, we know that it is opposite. So if A is equal to 0, so that indicates A. If A is equal to 1, so that indicates A bar. If it is B and C, if it is 0 0, then that indicates B plus C. Okay, it indicates B plus C bar, B bar plus C, and B bar plus C bar. Okay, so this is all about the variables which we can form here. Now let us try to see what are the inputs that we can keep. Okay, so similarly we can have the min terms like from 0 1 2 3 4 5 6 and sorry, max terms. So we can have the max term from 0 to 7. Okay, because we are considering the POS form. Now let us try to see the similarly, I just told you about the SOP. I can have the inputs, like 4 inputs are possible here: I0, I1, I2, and the I3. Okay, so again, the number of columns that represents the how many inputs we need, and what is the order of multiplexer that we can implement based on this one. And similarly, just like I just told you, if like, let us see the encirclement of like this only. Okay, so what will be the input of this multiplexer? So the input will be like A. Okay, so that will be A, and here, like, both are encircled, then it will be 1. Okay, so and then we can also see, and similarly, just like if you have like this one is the A bar, so this is how it will be. Okay, so this is how you can do that. Okay, one more thing is important here, like if I'm talking about the POS, because we are making pair with logic 0 in the POS form. So if both are encircled, in that case I need to connect this with the grounded. In none of are encircled, then I need to connect with the 1. So this is opposite to the SOP form. So the only difference is, like, yeah, just if you see here, this one is complementary to this one. That's it. There's no problem here. Okay, and so this is how we can connect. Okay, so this is the SOP and POS form. Now let us take some example and try to solve some question, and then that will help you to. So suppose I have a function something like this, ABC, and here I have a 4 min terms which are 0 2 4 and 6, and I want to implement it with the help of 4:1 multiplexers. So how we can do that? Let us try to see. Yeah, so here I have that number, and the number will be like 0 1 2 3 4 5 6 and 7. Okay, now if you try to encircle here, 0 will be encircled, and 2 will be encircled, 4 will be encircled, and 6 will be encircled. Okay, now if it tries to see here, this indicates the I0, this one is the I1, this one is the I2, and this one is the I3. Okay, now because 0 and 4 are encircled, and so that will give you the logic 1. Okay, 1 and 5 are both are not encircled, so that will give you the logic 0. 2 and 6 are circled, so that will give you the 1, and 3 and 7 are not encircled, so that will give you the 0. So this is the simply what you can do. Okay, and if you have the multiplex or something like this, so what you can connect, how you can connect, the simple connection could be like I0 and I1 will be I0 and I2 will be connected to the logic 1. So this one and this one will be connected to logic 1, and I1 and I2 will be connected to logic 0. And here I will have B and C, and enable will be connected to the grounded. Okay, and this is a simple circuit for this particular example. Okay, any doubt on this, anyone? If you have any doubt, you can ask the question. Yeah, this is really very simple, and it's very easy and interesting, right? So this is how you can make. Yeah, let us take one more example. Okay, yeah, I just told you about there are like if I have a 3 variables, so the possibility could be like I can use the MUX with 3 control signal or 3 select line, MUX with 2 select line, and MUX with 1 select line. And I just told you if I have a 3 variable, so how you can design a MUX with 3 control signals or 3 select lines. Okay, so this was very easy, just based on the input combination, you have to just make it logic 1 or 0. So the minterms which are present, that you have to connect it with the logic high, and the minterms which are not present, then you have to connect those with the logic 0. And the second possibility, like you can go for the 4:1 MUX. Another possibility could be like, because I have a 3 variable, so I can make it with the help of 8:1. Second possibility could be 4:1, and third possibility could be 2:1. 8:1 is very easy. Okay, all the minterms which are available, that I have to connect those inputs accordingly. 4:1 we have already done like this. So like this you have to do for the 4:1. Now let us talk about how you can make for the 2:1 and how the circuit looks complex from inside and the outside. Okay, so let us try to see what are the different possibilities. Yes, one more thing, it is not necessary, like see here, if you see this case, in this case A is acting as an input. Okay, what should be the input? A decides what is the input, and B and C decide what is the select lines. Okay, so BC decide the select lines. Now if we change the order, I'm considering here A is the MSB and C is the LSB. Okay, so if we are changing the order, so might be this numbering 0 and 1 will also change. Okay, so let us try to take that example and try to see how it is. Suppose I have a decimal 3 variable, and the total possibilities are 0, 0, 0 to 1, 1, 1. Okay, so these are the possibilities. I'm considering this A is the MSB and C is the LSB. Okay, after considering these things, let us try to see what are the different possibilities of MUX input table that we can have. Okay, so let us try to see here. If the order is like this, because A is MSB and B and C is there, so A, B, C, they are following the order whatever I have here, A, B, C. In that case, the numbering will be like what we have already done: 0, 1, 2, 3, 4, 5, 6, and 7. Now let us take one more example. If see, it is not necessary that you can always keep A as an input. You can keep any of the variable as an input and rest other input as a other variable as a select lines. So it is also possible. If you see here, I am considering A and C as a select line and B as an input. Okay, so in that case, can anyone tell me what will be the numbering in this case? The numbering will not be same as the first table.
So the first one will be 0, and the down one here is 1.
1. There will be 2. Yeah, so if you see here, this terms give 0, 0, 0, 0. No. This B is 1, right? Here, B is 1. So this combination
C should be 1. Sorry.
So this will give you, like this cell will give you 0, 1, 0, and 0, 1, 0 means this is not 1. This is equivalent to 2. Okay, So
this again that will be 1 like the previous one.
yeah, so yeah, that will be 1. Of course, it's no 0, 1, 2 will be here,
Yes, sir.
3 will be here, 4, 5, 6, and 7. Now there is a very interesting problem here now. If we can go back to the previous slide, let us try to see. In the previous slide, we had a variables like we had the min term 0, 2, 4, and 6. And if I am considering A as an input and B and C as a control signal, in that case, 2 of the inputs were connected to logic high and 2 of the inputs were connected to logic low. Okay, and logic 0 and 1 is available with us, like VDD and ground is available with us. So we don't need any of the logical gate to implement these inputs. Now there is one trick here. Now let us go back. Let us consider the next example which we are doing here. In this table, let us assume the same problem. The problem was 0 to 4 and 6, right? I think it was the problem 0 to 4 and 6. Yes. So let us assume if the function is same, A, B, C, and that is 0 to 4 and 6. Now let us try to see if I'm considering B as an input and A and C as a control line or the select line. So how it will happen, how it will be decided. Let us try to see here. 0, 2, 4, and 6. Okay, again you are getting the same kind of pair. Okay, so here the B will be connected, but there may be some change in the logical structure. There may be some change in the logical structure if there are something different. Okay, so let us take one different example. For example, I have a function A, B, C that is summation of M 0, 1, 5, and 6. Yes, let us assume this one. Okay, if this is the example, in that case, what will happen in the both the cases? Let us try to see. In the first case, I will have 0, 1, 5, and 6. So this will give you the A bar. This will give you the 1. This will give you the let us assume 6 is not there. Then let us try to see. Okay, 6 is not there. Then what will happen? This will be 1. This will be 0, and this will be 0. Okay, so what we need? We need I0 should be connected to the A with the help of one inverter. So the circuit will be something like this. 4 inputs, I0, I1, I2, I3, and I0 will be connected to the A with the help of one inverter. I1 will be connected to the grounded, and these both will be connected to the 1, and both other will be connected to the grounded. And this is how we will get it like B and C, and this is the output F. Now let us consider the second case. In the second case, and considering the function is same. Okay, 6 is not there. Okay, function is same. 0, 1, 5, 0, 1, and 5 is there. So 0, 1, and 5 is there. Okay, and if we try to see this one, what it says that the I0 should be connected to the B bar. Okay, I1 is connected to the B bar, and I3 is connected to the B bar. Okay, so what it means, the logical design will change. Means the design will change. I0, I1, I2, and I3. Okay, so if this is the case, so first, second, and fourth will be connected to the B bar. This is the B and B bar, and this one be connected to the logic 0. And here we will have a and C, and function is something like this. So this is how the structure will look like. So the same function can be implemented in the different way, and that decides, like that depends which of the variable I am considering as a control signal or the select line. Okay, so this is something important that you should know. If you have any doubt on this, you can ask the question. Okay, so this is how you can implement with the help of two different possibilities. Yeah, there could be another possibility, like you can keep C as an input and A and B as a as a input lines, like they what select lines. Okay, so other possibility can also be considered. So yeah, so if you have any doubt, you can ask the questions. Otherwise, I can explain some other possibilities as well. Okay.
Excuse me, sir.
Yeah.
Sir, can you please upload the lectures on LMS?
Yeah. So please give 1-2 days time. I will edit it. I will try to get some time, maybe 2-3 hours. Then I will try to update all those things. Okay. Maybe today or tomorrow I will do that. Okay, fine. So I hope these points are clear, like how it is working and how you can design. Other possibilities are also there, like you can make the this table in a different way. Yeah, this possibility could also be there. You can keep C as an input and A and B as a select line. So the numbering will be 0, 1, 2, 3, 4, 5, and 6, 7, something like that. Okay, so this is possible. So all the possibilities what we are seeing over here, that required 4 number of inputs, means whatever the function I will get, whatever the output I will get, I need to implement all these with the help of 4 raised to 1 mux. Okay, with the help of 4 raised to 1 mux, I can do that. Now suppose I want to design same function with the help of 2 raised to 1, then I have to keep 2 columns only, not 4 columns. Okay, so in that case, what could be done here? So this is one of the possibility. I can keep A and B here and C here. So C will decide the select lines and A and B will act as the input lines. Okay, so here I will have a 2 input, I0 and I1. Okay, so and accordingly you can mark the numbers, like where the numbers should be. Okay. So the numbers are based on this one. Similarly, other possibility could be like B, C, and A. In that case, number will be like 0, 1, 2, 3, 4, 5, 6, and 7. Because A is, I am always considering A as a MSB. After considering this, the table could be something like that. There may be one more possibility. I can make it like C, A, and B. This is also one of the possibility. So where I can keep 0, 1, 2, 3, 4, 5, 6, and 7. So this is how you can make the numbers. So it is not necessary that what arrangement you are making, like ACB or ABCA, whatever you are writing, the function will be same. Like there's no effect your unit, like you will get the same kind of outputs. Okay, so these are some of the possibilities. So to implement the function based on the below 3 tables, you can use 2 raised to 1 mux. So 2 raised to 1 mux will be sufficient. But one more thing is that what is important thing. Let us talk about the previous function only. Okay, the previous function was something like f a b c was summation of, what was that function? Can anyone recall? It was, I think,
0, 1, 5.
0, 1, and 5. Okay, 0, 1, 5. Now, if I have to design the same circuit or same function with the help of 2 raised to 1 mux, then what will happen? How it will be designed? So let us try to see here. 0, 1, 5 means what? 0, 1, and 5 here. Okay. So if you see here, the input to the mux will be like this, whatever the E here. So the I0 will be connected to the A bar, B bar. And I1 will be connected, like if you see these two, if you simplify these two, what will be the function? A bar, B bar plus A, B bar. Okay, so you can take B bar, you can take common, like A bar plus A, and A bar plus A, that will give you the logic one. So B bar should be there. So the I1 will be connected to the B bar. So this is how you will get it. This is how you can make the table. Now if you see, if I am utilizing 4 raised to 1 mux to design the same function, so that we need 0, 1, and 5. Okay, and here I need A bar and logic 1 and 0 and 0. Okay, so only one inverter is required in the first case. But in the second case, if you see, you need two inverters for A bar and the B bar and one AND gate also. So the hardware requirement will be more. Okay, so if you are reducing the number of inputs to design any of the combinational logic or combinational function, in that case, the hardware cost or external hardware cost is going to be increased, because you have more possibilities here to make the combinations. Okay, so these are some of the important things that you should know. Anyone has any doubt on this? If you have any doubt, you can ask the questions. Okay, yeah, the similar thing can be done. Okay, so now if you see, the good thing is, like, you can, if we are using 4:1 MUX, then the external hardware requirement will be less. Okay, and if you are using 2:1, external hardware requirement will be more. So the question could be like, which of the combination will give you the optimum hardware, external hardware requirement? So that 4:1 will give you the optimum one. Now another question is, because I have a 3 variable, and in 3 variable, there are 3 possibilities that I can have: 8:1, 4:1, 2:1. And in 8:1, you do not need any of the logical gates. Just you have to connect input with logic high or logic 0 based on the minterm available. So none of the hardware, external hardware, is required for the 8:1. Okay, but in case of 4:1, you need some of the hardware. And so what it means, as you keep on reducing the order of multiplexer, the external hardware requirement will also increase. This is really very important point I'm saying. Okay, the external hardware requirement will increase if you are reducing the order of multiplexer. Okay, higher order multiplexer will require less hardware. External hardware, I'm talking about the external hardware. External hardware means out of this multiplexer. I have the multiplexer, and outside this multiplexer, how much hardware is needed. Now the question is, what about the internal hardware? Okay, suppose one function I'm implementing, like if you see the same function here, whatever the function I have, if I am utilizing 8:1, so what I have to do, I have to connect I0, I1 and I5 to logic 1 and rest all other inputs to the logic 0, and this is what I can make the function. Okay, for 4:1, I need only one inverter and one input to the ground and two of the input to one input to the VDD and two inputs to the grounded. Okay, so one external hardware is required. But if you see the inside hardware requirement, 8:1 multiplexer required at least double number of gates, logical gates inside the module than 4:1. So the total area penalty, if we consider the internal and external both, the 4:1 may be the optimum one. Okay, so 4:1, considering the 4:1 multiplexer to design the same function will give you the overall less area penalty than 8:1. Okay, so please recall what I'm saying. This is really very important to understand. Okay, if you have any doubt on this point, you can ask the question again, what I'm saying. Internal and external hardware requirement. Okay, so this is important, and these are very tricky questions actually, what I am saying. So these kind of questions may come in the gate examination. Okay. So you know, like how many gates are needed to implement 8:1. You also know how many gates will be needed to design 4:1. So you know the internal structure, and from the function you can decide how many external logical gates are required, and then you can comment on the hardware requirement penalty and something like that. So this is really very important. Okay, so if you have any doubt, you can ask the question, otherwise we can move ahead. Anyone? Arpit, doubt is clear? Is there any doubt?
Yes, sir. No, sir.
Okay, fine. So
Sir, I just, sir, one doubt,
yeah,
sir.
Yeah.
So
Right.
we have to consider the internal structure, like number of gates in each we should know if we want to solve quickly.
Can you repeat the question again?
So like 8:1 required some number of gates, and then 4:1 required. So we need to know it priorly if we want to solve it quickly, so that we can decide the internal number of gates required
So
per
it
unit.
completely depends on your problem statement. Like they are asking about the overall hardware requirement, or they are asking about the external complexity. So based on that, you can decide like which of these will be more suitable. Okay. So one very simple thing is, as I just told you, if you want to reduce the complexity outside, then you have to use higher order multiplexer. And if you want to reduce the complexity inside, you have to use the lower order multiplexer. Okay, but the problem is like, see, you cannot comment, like the hardware requirement depends on the logic function. There is no direct relation on that. Okay, the logic function, if you are changing the logic function, and even though you are using 4:1 multiplexer, might be the hardware requirement for two different functions will be different. Okay, so this can happen. So you got the point? You asked the same
Yes,
thing?
sir. So overall hardware requirement can be variable according to
Yes,
the
yes,
function.
yes, yes. It is not fixed. There is no straightforward relation with variable number n, m, or something like that. There is no relation. You have, it depends on how many minterms we want to execute by with the help of that multiplexer. So if
Yes,
the
sir. We
minterms
have to
are
compare every case one by one.
yes, so this is really a very good problem statement for you. Like I did not try it. Might be there could be relation, because I have not tried, so I cannot comment on it. You can just consider the different minterms. Like, see, yeah, I'm just giving one homework. Let us consider I have a function which is xyz. Okay, and the possibility could be like one minterm is there, two minterm is there, three minterm is there, and seven minterm is also possible. Okay, so there are many possibilities. Either zero is there, either one, two is there, three is there. So there are many possibilities. Okay, and like total possibility could be, I think, 2 to the power 8. Okay, so this much of possibility you can have. Okay, so just try to check, just take some sample of inputs, like you can activate only one input, and just try to design with the help of 4:1 MUX, and try to see how much complexity, how the complexity is going to vary. Okay, so based on that you can comment. So you can check it out at home. I have not tried, so I cannot comment it. Maybe there may be some relation with the help with input, min term, and the max terms. There may be some relation, but I need to check it out. So I'm just giving you as a homework. You just check it out. Might be you will get some answer. So I'm expecting, in the next lecture someone will come up with some relation with a number of input in the multiplexer and the variables in the function. Okay, so please try to check it out at home, and maybe we'll get something. Okay, your point is clear, right?
Yes, sir.
Okay, fine. Now, so this is all about how we can design the multiplexer. Yeah, here we have another problem. Suppose I have a POS form which is given something like this, and I have to use it with the help of multiplexer. So how we can design this thing? Okay, so let us try to design it. Okay. So the maximums are here. Yeah, let us try to first write the numbers. So the numbers will be 0, 1, 2, 3, 4, 5, 6, and 7. Now I need to check what are the different maximums which are available here. So maximum 0 is there, maximum 1 is there, maximum 3, 5, and 7. Okay, so these are the maximums. Now if we need to talk about what will be the input of the multiplexer. So I have considered I0, I1, I2, and I3. So what will be the input of multiplexer? I0, I1, I2, I3. Can anyone comment on this? What will be inputs? I0 will be
X bar.
I0 will be X bar. How?
X.
Yes, sir. X according
It will
to
be X.
SPOS.
Yeah, we are talking about POS. So that will be opposite to the SOP, right? So the input I0 will be X. I1 will
Zero.
be, that will be
1.
0. Okay, I think who is saying 1? Because you're saying.
Yes, sir.
Okay. And who is saying 0?
So me.
Okay. The correct answer is because see here, we are considering POS form, not the SOP form. If you see the function, the pi symbol is there, right? So if we are considering the POS is opposite to the SOP. Okay, so if all the numbers are circled, in that case, that represents 0, not 1. Okay, this is opposite to the SOP. Okay, so here it will be 0. If none of the numbers are encircled in the column, then I need to keep it as 1. And if both are encircled, then I need to keep it as a 0. Okay. Okay. So this will be the input to the MUX. So Vikas, your doubt is clear or not?
Yes, sir.
Okay, fine. So if we try to implement the function, let us try to see how it can be implemented. Okay. So I0, that will be connected to the X. I1 and I3 will be connected to the grounded. Okay, or 0, logic 0. You can keep anything. It's not, yeah, let me keep logic 0 only. Okay. So these two will be connected to the grounded, and I2 will be connected to the logic 1, and this will be Y and Z. And so this is how a simple circuit can be implemented. Similarly, the homework is just try to implement the same function with the help of 2 raised to 1 MUX. Okay, so with the help of 2 raised to 1 MUX, try to implement the same function, and you will get how it is complex than the other one. Okay, so here is one question which I am giving. Yeah, see here, because I have a 4 variables A, B, C, D. So I can design this function either with the help of 16 raised to 1 or with raised to 8 raised to 1, 4 raised to 1, and 2 raised to 1. Okay, so these all are the 4 possibilities that we can have. Okay, so just I am giving you the homework. Just try to design this function with the help of all 4 possibilities.